Good afternoon, everyone. Welcome to this week's KET seminar. Today, we are excited to host Professor Juergen Rauleder. Professor Rauleder leads the Computational and Experimental Rotorcraft Engineering and Aerodynamics Lab at Georgia Tech. He is an Associate Director of the Vertical Lift Research Center of Excellence and also serves as Director of the Large Harper Wind Tunnel. His technical expertise is in experimental and applied numerical aerodynamics with a focus on rotorcraft and fixed wing applications. His research in international aerodynamics, aero-propulsive interactions, fluid structure interactions, and in piloted flight simulations is critical for design, efficiency, and safety of multi-prop electric aircraft and uncrewed aerial systems. Rauleder earned his bachelor's and master's at the University of Stuttgart and his doctorate at the University of Maryland. Please join me giving a warm welcome to Professor Juergen Rauleder.
Thank you very much for the introduction. Can you confirm that you can still hear me?
Yes, Professor, we can hear you.
And it's loud enough, or should I talk louder?
It's loud enough.
Yes. Loud enough. Okay. The last row says yes, so that's good. Thank you. Yeah. Thank you so much for inviting me to this seminar. As you heard from the bio, my background is in rotorcraft and fixed wing aeromechanics. So deep down in the electric VTOL world and the aviation world, and not so much transportation. So as such, I was doing my very best to leave no one behind in this seminar, so that there is a little bit for everybody, talking about bigger picture, broader interdisciplinary aspects of urban air mobility and advanced air mobility, with specifics to the vertical takeoff and landing designs that we see out there and the electric aspect of it, also hybrid electric aspect of it, its challenges, overall vehicle technology or overall urban air mobility or advanced air mobility, but also specifically the vehicle technologies, and then go into a little bit of the nitty-gritty of our research at the Serial Lab, where we talk about the aeromechanic challenges specific to electric VTOL vehicles in the AAM world. So for the first round of slides that are talking more about the broader perspective, I want to credit Mr. Mike Hirschberg, the outgoing director, or the Director Emeritus of the Vertical Flight Society, which is a society that which organizes important gatherings of the vertical flight community. It unites all of the professionals, or most of them at least, that are focusing on vertical takeoff and landing. It's there since, well, I'm not even sure exactly if Mike is on the line. Oh yeah, 1943 actually. I have it even on a slide. Silly me. It was founded as the American Helicopter Society, but as the name change suggests, we are the Vertical Flight Society now, and as such, we unite every aspect of vertical flight. So not only helicopters, which is only one kind of vertical takeoff and landing vehicles, and we talk about that, but we also talk about many other interesting vehicles today in the seminar. We are an educational association, as well as a trade organization, as well as a say lobbying organization to get more R&D funding from Congress, for the universities, for the research agencies, and so on. So with that little bit of background, I also want to go into some of the things that we want to talk about today. Like what is advanced air mobility? Now I looked it up. This is an AI answer. So, because your backgrounds might be very diverse from different kinds of, different sides of transportation, I think this is important to stress what all is advanced air mobility. And you see, it is a very broad definition. So it's an emerging aviation sector focused on integrating innovative, highly automated, and often electric, not always, but often, aircraft into the airspace to move people and cargo. So not only air taxis, but many other things in urban and suburban areas. So that's also something important as we talk about range later and how that matters to intra or intercity transport. And then aiming for quieter, more sustainable, and faster transportation. So all of those aspects are in advanced air mobility, and obviously that comes with challenges too. It's not all gold, of course, and we'll talk more about that as well. Just wanted to put it out there. What all is there in AAM? What is the definition? So again, the Vertical Flight Society, we can credit ourselves as and I say we because I'm very active in the Vertical Flight Society as the chapter president here in Atlanta and former Europe Africa regional director. Um, we can credit ourselves really of or for kicking this whole eVTOL revolution off. So you can really talk about an eVTOL revolution because that's what we have been seeing over the last decade and a half, really. It is a very fast development and started like this workshop down there on the lower photo. Not the historic one in 1944, which was the first AHS gathering, of course. Back then, we were only talking helicopters. There was nothing out there. Now we're talking electric vertical takeoff and landing, and they can take all kinds of shapes and forms, as you will see. Um, Only one, two more slides about us as Vertical Flight Society. Of course, I want you to become a member. So then you get the membership magazine for free. Students sign up for $25 a year, not a month, but a year. And so you can get the VertiFlight. You get that bi-monthly. And this magazine talks a lot about eVTOL, and so you will see a lot about the configurations we talk about today. You see them. We covered them in the past years, even decade, I would say. And as we go through these seminar slides, you find a lot of different configurations. Just two here, like a multicopter on the lower right and a ducted fan vehicle on the upper right. And there's a lot out there. As of October 20th, we have listed about 1,151 different aircraft, which are all kinds, vector thrust, lift and cruise, wingless, and other devices that sometimes take very interesting shapes. So that you know a little bit about what I mean by lift and cruise, what I mean by multicopter and those, you look at those, courtesy of Lilium, this chart, you look at those exemplary configurations. There's a lot of subkinds, but broadly speaking, we can actually dissect into different kinds. So multicopter design on the left, which is more like a helicopter, but it has many small rotors and not one large rotor. Then lift and cruise, second from the left. That means that we're using different means of propulsion for the cruise part, so forward flight, and for the vertical lift part, so up and down. So you have a propeller in the back, for example, or in the front that propels you forward. You have lifting rotors that do the lifting mission. And then one further to the right, the vector thrust is we're using the same propulsor that can be technically a jet, but most of the time, I don't know why that switched. Most of the time, it is actually uh, most of the time it is a propeller. And so you're using the same means of propulsion or the same propeller or prop rotor for the lifting mission, and the cruise mission, you just tilt them like a tilt rotor. And we will see that many of the current configurations are tilt rotors. And then to the very right is the configuration I've just shown as an example, multi-propulsor ducted fans. And there's a trade-off from left to right. So cheaper, costlier, lighter, heavier, long range, short range. What you can generally say is if you want long range, you need a wing. That's the reason why for longer range, there's always a wing. It produces lift more efficiently than a rotating wing or a propeller prop rotor. And that's why we see many of those have wings in addition to propellers or thrusters. Now, why not a single large rotor? We have done it for decades. That seems to work well, right? So at the end of the day, it boils down to the question, how long or efficiently do you want to hover? And you can see here why I say this on the chart on the left from a textbook. You can see that the helicopter ranges very highly here on the y-axis, which is the hover efficiency, because it has a low disk loading. That's thrust per unit area. So it has a large rotor that moves air slowly, and that's more efficient lift production. And so for that reason, vertical lift is provided better, more efficiently with a single main rotor. And hence a helicopter is a good hovering vehicle. There's nothing wrong about that. As we go further to the right, the efficiency, and this is not cruise efficiency, this is hover efficiency or vertical lift efficiency, that goes down as we go to smaller thrusters. So direct lift, tilt rotor, small diameter thrusters need more power. More power is bad, right? So why do we do it anyway? That has to do to a large part, not only, but also because of our mission, but also has to do with distributed electric propulsion. And that is something in aerospace that we have seen a lot, like as a big enabler in the last 10, 20 years. And what is this, right? And want to talk a little bit about why is this an enabler and why did it lead to smaller thrusters? So most configurations you will see today take advantage of this distributed electric propulsion or power by wire, so to say. It unlocks a lot of design freedom. You can put the thrusters where you want. You replace a single rotor with lots of small propellers. You put them where you need it, where they are most efficient and or where you have space for them. So you're not limited anymore in your design space when it comes to the propulsive system. Also, very, very importantly, hence bolded, it's better suited for electric propulsion because you can use many smaller, hence lower torque and lighter motors. And you put them right where the propulsor is, so right where the propeller, in many cases, is. And so you don't need any shafting. You don't need any very heavy structure that from the turbine engine to the rotor system or so, because that's weight. Can also be failure modes in there, so you don't have that. You produce the power by the motor, electric motor, right where you need it, where the propeller is. So then you need some energy storage, right? So let's talk only a little bit about energy storage. Batteries. Battery electric is not the only electric, and I will talk more about that. The problem with battery electric is you're limited in range because you have low energy density and low specific energy when it comes to batteries. You can do a hybrid electric, like you're using a diesel engine or you're using a gas turbine engine that provides shaft power that drives a generator, and that generator then either directly feeds your propulsors or your propellers, or it feeds a battery, and then that battery gives energy to the motor. So this dramatically improves range and payload, and then you can do hydrogen electric. This could be a major power unlock and can be clean, but there is some more research to be done to to have that as a viable solution. But I will show you some impressive numbers why that might be a good plan. Um, so overall, electric propulsion, be it batteries, hybrid electric, or hydrogen electric, is a gateway to decarbonization and therefore sustainable aviation. A little bit taxonomy here. Don't want to bore you with that, but there is urban air mobility that is more, it's intra-city transport. That is all of the areas here in not red, but well, kind of a very light red. That's the power sources and lift modes or landing, I should say, landing, takeoff and landing modes that you can pair. So for urban air mobility, battery electric vertical takeoff and landing is an option. For regional air mobility in blue, so that's here, this framed area, battery electric is not really an option if you want the vertical takeoff and landing capability, so no runway. That is because you need so much more power, as we have seen before. And so you need so much more power to vertical takeoff and land. So either you fly a short distance, which intra-city is okay, or you use a different, you give up the vertical takeoff and landing capability and you go to short takeoff and landing or STOL, or you go to conventional takeoff and landing. Now, you can do that, but then you need a runway. A runway might be not convenient in an urban environment, but it could be, like in suburban areas and so on, especially when it comes to short takeoff and landing, you need a short runway. That is feasible. Then you can do battery STOL. You're giving up, again, the vertical lift capability, or you can do hybrid electric or hydrogen electric. So, there are different ways you can combine all of this. Hydrogen electric, I said, why is this, could this be a game changer? Well, it increases range dramatically. As Joby, one of the big players here, has shown, they have flown their battery electric VTOL 150 miles, and then the same one retrofitted with hydrogen. They almost times four that range. So that shows you how much you can do with hydrogen electric. So using a fuel cell to generate the electricity, I mean. There are challenges, of course, right? And so some of them can be overcome or are already overcome. So technology, the batteries, thanks to the electric car industry, electric vehicle industry, we have pretty good batteries, but they could be better, but we can do an intra-city mission. Motors are there. If you want to get more economical, you need more passengers. So then it becomes a challenge again. Then you need larger batteries, motors, and so on. And then that becomes a challenge again. Now, infrastructure. So you need physical city planning, vertiports. You need high power structure to recharge the batteries and so on. So that all needs to be planned. That's a challenge. Then traffic management. The workforce, you need the engineers. Yeah, there's a shortage. Most of my cohort back from university when I was a grad student, they went to eVTOL companies. They work for Joby, Archer, Volocopter, all of those. They're not working, most of them, for Bell, Sikorsky, Boeing anymore. Many do, but actually, meantime, the eVTOL sector takes up a lot of that potential or a lot of that talent. Pilot shortage can be a workforce problem. Autonomy will take care of that, but then to certify an autonomous vehicle that transports people, that is more difficult. So there we are at the standards and regulations. They are largely in place, some of them still developing. So that is a challenge. And then for public acceptance, noise, I would say Noise and safety are number one concerns, and then the not in my backyard problem. So yes, everybody is for electric VTOL. Everybody is for leisure drones as well when they fly it and they take the greatest videos. But then, oh gosh, you're in the park and you want to relax and you have the zzz sounds everywhere, then you're against it. So not in my backyard. That is a major challenge. Um, just some vehicles that I wanna see, not or want to show you, not too much though, is these example vehicles that you may or may not have seen from Archer, Beta, Joby. They all have a wing, as you say, for as you see for range. As I mentioned before, they have tilt rotors to use the same propulsors for forward flight and for vertical flight. Now, that is the Joby. That is a vector thrust vehicle, only tilt rotor. But the Beta aircraft here, you can see there is a lifting rotor that can stop in forward flight, and then you can propel it forward with the propeller, and the lift generation is done by the wing, and the wing is more efficient in lift generation. Hence, that's a good plan to have a wing. Um, so the Archer vehicle is kind of a hybrid between those. Then some other front or some other eVTOL companies that are up there, Vertical Aerospace from the UK, Supernal well, they're actually discontinued meantime. Um, there's a lot of players in the field. There's also smaller international aircraft, the Volocopter Skydrive or EHang. And EHang has a certification. They're flying. And in China, a lot of things are flying. There's really like an explosion when it comes to these designs. And the EHang vehicle on the left, I've seen it in person. Uh, that flies, fully certified. So there's a lot going on in China too. So because we don't have a lot of time, I also want to spend a little bit of time on the aeromechanic challenges of all of this, right? We have talked about the vehicles, we have talked about the different kinds of configurations that you have that you see out there, and there are aeromechanic challenges, and that's my bread and butter, right? So these are complex vehicles with complex interactional aerodynamics between the propulsors, which are mostly propellers, and the lifting system, which is the wing. So also called aero-propulsive interactions. So whenever the lifting system interacts with the propulsive system. And that's very poorly understood. And that's a problem. You need to know these interactions for vibration, fatigue, for efficiency considerations, for optimization of your vehicle. You need to understand these interactions. And we in my lab are looking specifically into tilt rotors, because a lot of those vehicles use tilting rotor systems. The conversion maneuver between vertical takeoff mode, if you look at my video, like vertical takeoff mode, and then the transition to forward flight, which a helicopter more or less does easily, that's a bit less, more complex mechanically for a tilt rotor. And we don't know so much about what's going on aerodynamically in that complex aerodynamic regimes. So although this is safety critical. Also, I show you some simulation results, but also wind tunnel tests, because we cannot measure everything. We need a model, but then we need models that to be validated. So hence we need the wind tunnel research again. And so you will see that my group is very focused on both the simulation part and also the validation through wind tunnel results and getting some insights by the measurements alone. So one of our test rigs is this multi-tilt wing design. So one wing, but multiple tilting props or tilting fans. And we are rotating the props around the wing so as to simulate a tilt rotor transition maneuver. We're measuring pressures. We're measuring, it should play a video as we are doing the transition maneuver. So we're measuring pressures, we're doing flow fields, and we're measuring loads, as in the lift, the drag of the wing, what is efficient, what is not. Not going to bore you with too many results, but one point I'm going to make is that you need to predict or measure things, not only not only the effect, but also the cause. So the effect is a lift change, for example, or a drag change of the wing. But the cause for it can be many different things, and hence you need to know what the aerodynamic flow field looks like, and that's what we're doing with flow field visualization, with either smoke, um, or with particle image velocimetry. And the video on the right here shows such a test. The prop is coming on. You see where there's flow structures, tip vortices from the prop, they're hitting the wing. That will generate unsteady forces and moments that are important, and you need to understand if you are to develop a safe vehicle. How does this measurement technique work? Well, you're doing image A, image B, you're correlating them, and then you're measuring thereby the velocity vector. And you get flow fields like the right, like shown on the right. There's the tip vortex. I go to a laser pointer here. There's a tip vortex here. So that's a rotational flow that comes from the prop, and the prop wash goes over the wing. It will generate unsteady forces moments, and it will generate more lift than you would normally see. This is a video of a transition maneuver on the left. We're transitioning this prop rotor around the wing, and as you can see, the flow goes with it. Of course, it does, and it will generate all of those unsteady forces and moments on the wing, and you need to understand those when you design such vehicles. It also leads to unsteady dynamics that are safety critical. I'm trying to get my here out of this. Okay. Again, a transition maneuver. Now we're averaging the flow a little bit. And so we're getting rid of some unsteadiness in the flow. So as to get the mean forces, as to get the mean velocities, that is showing you some different perspective, but you're neglecting the unsteadiness in the flow. And so depending on what you're interested in, you may or may not do some averaging as you go along. I will, in the interest of time, I will skip through that quickly. So again, this is looking at one instance in time during the transition corridor. So 45 degrees tilt angle. You're in the middle between going from vertical lift to forward flight. And you can see that there's many different ways, at least 3 different ways we modeled it in my group here, from low fidelity to high fidelity in computational fluid dynamics. And then we compared it to wind tunnel measurements. Why we're doing this? Well, because you can simulate everything you want. If it's not validated, it's not worth anything, because you don't know if it's right or wrong, right? So you need to validate it by wind tunnel measurements on the right. And we can see that you need a certain level of fidelity in the simulations to catch everything right. Well, why is this important? It is important because it changes the air loads, so the lift and the drag, the unsteady forces and moments, and hence also your longevity of your product. Also, your ride quality suffers if you have a lot of unsteadiness there. And so that's why we're looking into this, because everything changes all the time if you have a propeller interacting with a wing or a prop rotor interacting with a wing, and especially when you go from vertical lift to forward flight. Now, propellers or prop rotors interacting with wings is not the only use case that we're looking at, but there are a lot of different ways you can have a lot of different propulsors you can use. So some of the vehicles out there, they're using ducted fans. I said for noise considerations. Also sometimes for efficiency and safety. And so we looked into the aero-propulsive interactions or interactional aerodynamics between such an electric ducted fan and the wing. And this shows you the test setup. And we have shown that if you're careful with your integration, leading edge versus trailing edge uh, electric ducted fan, if you're careful with the placement, you can actually win a lot of extra lift, up to 153% increase over your wing alone. So because you're blowing over the wing, you can generate additional force, additional lift force, and that helps you with short takeoff and landing, right? So remember, that's my 5 minutes left kind of alarm. So the regional air mobility, which might be, interested in short takeoff and landing capability, uh, having extra lift on the wings means that you're taking off sooner, shorter runway. So you want that, right? But you can only do that with very high angles of attack. And the high angle of attack is enabled by these electric ducted fans that are installed on the wing. And so, why is that? Why does it generate this extra lift? We've done again our flow field survey, our velocity measurements, time resolved with high-speed cameras and lasers. And we see that at low angle of attack, 10 degrees, everything is in good shape. Flow is barely separated. So you should look at my laser pointer. Incipient separation, no problem. But then you're going to a higher angle of attack, flow massively separated if there is no propulsor. However, you put that electric ducted fan, and again, these are measurements from the wind tunnel. You put the electric ducted fan on your wing, and you have killed the flow separation, actually delayed it to higher angles of attack. And that's exactly what you want for a short takeoff and landing vehicle. And then if you go a little bit further, higher angle of attack, the flow is super, like is fully separated, but even more than at 30 degrees, of course. And you're sucking that into your propulsor. So you get some additional thrust of the propulsor, but you are stalling the wing, and so you are losing lift. So you may or may not want that. And the last little, and that's only a small section that I want to talk about. The last little thing is not ship deck landing. I'm using that as a parallel to a eVTOL or AAM vehicle landing in a city because there's a lot of things similar going on here. You have a solid structure like the vertiport, a ground structure, and a wall structure, in this case, a hangar. In the eVTOL world, it would be actually a building standing next to you, right? You're doing a landing maneuver and you see a lot of interactional flow. You have partial ground effect, full ground effect that helps you, but also it produces a lot of unsteadiness, and the pilot or autopilot needs to correct for that. And you're getting a lot of these here to the right, a lot of these complex effects that you need to model and that you need to do measurements to understand those things. And those are very similar to what's going on in the eVTOL or AAM world when you're actually landing in a city, because all of those structural interactions with solid structures. So we've modeled those. We have put wind tunnel measure or did wind tunnel measurements, and we have validated those things as well. And we also have done other things that are very important for eVTOL and for the for that stop that video. Yeah, that are important for AAM and eVTOL. For example, multi-rotor interactions, downwash, outwash. So that's the flow that we accelerate and push down. That interacts with ground personnel, with infrastructure. If you have boxes, cargo or so, they could be impacted by that. They could move. So you need to understand those things, and that's why we're looking at that in the wind tunnel. We're looking at it in the in simulations as well. And those things are highly relevant for AAM as well as the city flows, right? So we're doing simulations in the city, quick turnaround using our Lattice-Boltzmann solver that we developed. And you need to fly in those environments. And that's where the ship comes in again. It's highly interactional, unsteady, and you're interacting with ground structure that sheds turbulence and vortices. So very similar problem as the ship landing. That's why I was bringing it up. And then other oh, I want to play that video because it's very cool. And you have seen this the last slide. For some reason, I cannot. Mm. Hmm. Okay, well, ah, I've, well, okay. It's too complex for me. Professor having problem with the technique, but um,
Professor, sorry,
with,
what if you reshare the screen? Maybe that way,
what's that?
maybe if you reshare your screen, it stops
Ah,
sharing again, maybe that way.
oh, that's, yeah. Well, let's see.
Can I hear?
Nah. Well, since we're okay, I think now it plays. Hmm. Okay, I give up, but uh, I want to point out here on the left, sea gliders are another mode of transportation. The Regent Aircraft Company from Rhode Island is developing a sea glider, for example. So that is to develop, again, transportation. That's the audience. Some other interesting area where developments are going on. You're flying in ground effect, and a lot of interactional aerodynamics are happening, and that's why we're looking into this with this sea glider vehicle on the left. So that's really all I wanted to say. The video is cool, but you can kind of gauge what's happening there. A lot of unsteadiness coming from the waves and hitting the wing, and that would generate unsteady forces. And so you need to have them under control if you were to develop such a vehicle. With that, I'm at the end, and sorry about the struggle at the very end with that video. And I'll open the floor for any questions that the audience might have in the room or online.
Thank you very much, Professor, for your presentation. Now we're going to have some time for questions. We have some questions from the audience. Yes, Akash, please.
Thank you, Professor, for the presentation. It's a very interesting field, and I'm not that knowledgeable. So I wanted to ask if the attack angle also affects the fatigue life of the blades that you're using, because it might change the stress concentration and distributions on it.
Are you talking about the angle of attack of the wing, so the fixed wing, or of the propeller blades?
It affects more, I guess.
Because when I was looking at the electric ducted fan on the wing, that wing was not moving, so you're not really concerned about that aspect. But if you have high angles of attack, then you will produce flow separation generally, and that's very unsteady, and so it will produce some fatigue loads. And you can have them in rotating, like for rotating blades, as well as for fixed wings. For fixed wings, though, you only really have the high angles of attack during takeoff and landing. That's it on the runway, right? And so you're not really concerned about that because it doesn't have it happens twice per flight. But for a rotating wing vehicle, so with propellers changing their, or a helicopter rotor changing their pitch angle or the angle of attack around the clock all the time, there certainly the high angles of attack will have a effect, a big effect on the unsteady loads on the air, on the unsteady air loads on the blade, and hence also the longevity or the fatigue life of the blades. Absolutely.
Do you have more questions? Yes, we have questions.
So thank you so much for the nice presentation, Professor. My first question is that do you think that the autonomous aerial mobility can complement the ground freight system? And you showed these nice simulations for the city. So my question is, do you think we need changes in the city infrastructure for the mass application of these drones?
Yes, absolutely. And you're hitting on a very important point there because if this, advanced air mobility, which includes cargo, and air taxis, if this is to succeed economically, then there must be lots of those vehicles operating all the time. And only then is economical, really, in my view. And I'm not doing the math here. I'm not even having an MBA, right? I'm not doing the dollar math equations, the dollar calculations. But we want or envision a mass transportation and a mass drone delivery. And so, yes, then it becomes a struggle to integrate that into not only the airspace, but also the ground infrastructure. It means you need lots of vertiports. You need, or big vertiports where you can land. You need ground stations for the drones where they can land. In China, that's already a reality. A friend has shown me a video. He ordered a coffee. It was there a minute or 1.5 later. It was hot. It didn't spill. He walked to a ground station. The drone came down and it delivered his coffee. And so if you take that to the next level when it's really economical, yes, a lot of challenges with the integration. And I think it can be done, but you need municipalities talking with the aviation folks. Then you need to talk with the mayor, of course, and the architects and the civil engineers that build the ground infrastructure. And you need to have them all in the same room, and they all need to share the same vision. And then there will be neighbors that are against it, right? And that can be agencies, it can be private people. And so, yes, it's a challenge.
Thank you.
Thank you. Yes, sir.
And thank you so much, Professor, for sharing. I have a question. I can imagine in urban AAM operations, the aircraft may fly near the bridges or tall structures where crosswinds and the turbulent flow can be intensified. So my question is, such scenario can be reliably captured through simulation, and how to evaluate whether our aircraft can maintain the stability and safety under this disturbance? Yes, that's my question.
Yeah, very good. Excellent question. So yes, you're absolutely right. There are, just as suggested in this snapshot in the middle there on this slide, there's a highly turbulent environment close to those buildings because there's a wind, especially if the building is higher, there's a lot of wind. and very, very unsteady flow. And that is definitely a challenge. And if I go back here to my to my uh, to my well, one of the videos I didn't show here, it should hopefully it plays. Yeah. So it's kind of out of phase. So I will. Whew, really challenged by my laptop today. So to one of your, because I think your question was really multifaceted. So one of them was, can you accurately predict it, and how do you make sure it's accurately predicted? That you can only do by comparing it to experiments, and that's why we're doing, for example, the ship deck landing test. We're running a rotor into this, or in a landing approach, and you can do the same thing with a quad rotor drone or any kind of eVTOL vehicle. If you have a subscale model, for example, you can put it in the wind tunnel, and it's a very and then you do this approach, and it's a very similar scenario. So it's you're doing the experiments and then you're validating your model. I'll get to your last part of the question also. You will encounter those scenarios. So your rotor comes close to that heliport or vertiport, and then it interacts with the ground. And we're on the red line here on the right. We have a minimum of thrust, and or delta thrust over the trimmed. I don't want to go into the detail, but the point is, it changes over time as we fly the maneuver. And so the pilot or autopilot need to be ready to counter those changing forces. And how do you make sure that they have that? The pilot needs to be trained, fine. The autopilot needs to know what's coming, or at least be having the control authority at their fingertips to be able to counter that phenomenon, whatever it is. So if I play the video further, I see that I go closer to that wall structure, and I see that there's a recirculation happening, and that interacts with my rotor thrust. So there's an up and down movement on the right curve for the thrust, which is the upper one here. Up and down movement. That means that in this instance, the pilot would need to react very quickly to give the command to give the propulsor the command to do more or less thrust, so that they're not crashing into the ground, or they have to give a command to counter those pitching moments to not crash into the hangar, because that's what we have shown is happening. And these are validation maps, basically, where we've shown that that our simulation LBM here is lattice Boltzmann method. It is our simulation tool compared with experiment. We're showing that we're getting the same pitching moment maps when we're doing the maneuver compared to the experiment. That's how we validate it against experiment. But to your last point of the question, and I touched on it already a little bit, how do you make sure that you're still safe? You need to do the measurements and the simulations to see, okay, what's really happening? And then you need to see, okay, how much delta thrust, how much delta moment, and so on do I need? And then is my installed power, like my electric motor and my propeller or my ducted fan or whatever it is, strong enough to produce that little extra thrust? So you need to know these things to be able to produce, to be able to design for this extra thrust, and to do it quickly enough so that the pilot reacts or the autopilot reacts and the engine reacts quickly enough. And so that is basically the last part of your question, and hopefully I got the I answered all your questions that were hidden in this in this one.
Thank you so much. Yes.
If it is okay, we're gonna address a couple of more questions.
Yeah, of course.
Yeah, thank you, Professor, for the presentation. Mine is just a question based on some information that I came across. So at the Consumer Electric Show in Las Vegas last month, there was a company from Finland that has two technologies. The first is a in-wheel thrust motor that actually helps to improve conventional powertrains. But the second, which is really more interesting, is a solid-state battery that's 400 watt-hours per kilogram density. That together, I think, would probably improve the efficiency by more than 100%. So I'm just wondering, because I saw your battery options, are you considering things like a solid-state battery, and to what extent would that change your design? Because I think it would really improve the thrust.
Yeah. So I'm not a battery expert, and so I don't think I can answer your question, but the better the battery, the better, right? If you have a 400 watt hour, or what do you say? 400 watt hour per kilogram, I think you said. That is, of course, that's very good. And so the higher the energy density, the better. It will allow you so much more, design freedom, with those vehicles. And you can fly further. So to this chart here, then, maybe the battery electric option, now that, with the 400 watt hours per kilogram, maybe that is now actually attractive also for other segments, for regional air mobility all of a sudden. It's possible if you design your aircraft very cleverly with a lot of those batteries, maybe the regional air transportation, or the RAM, regional air mobility, is actually feasible with that. Possible.
Thanks,
But then
Professor.
again, I'm not an ecosystems guy, and also not an electric battery guy. And so take my answer with a grain of salt. There might be people that disagree. So, I take my answer like as a hypothesis.
Thanks, Professor. We have a couple of questions in the chat, so I will go ahead and read them.
Yes.
So the first one is, how does lower rotor speed while maintaining disk loading, high solidity airfoil affect energy transport in the tip vortices? And the second one is, how do you conserve tip vortex energy in the LBM codes?
Okay. I didn't hear the full first one. Can you repeat the first one?
Yes, sure. So how does lower rotor speed while maintaining disk loading, high solidity airfoil affect energy transport in the tip vortices?
So that's a deep down aerodynamics question. If you do, so the tip vortex strength is proportional to the air load that the blade carries. So that air load, or lift load, whatever you want to call it, is higher, either because you're rotating faster, or because you're pitching the blade more. So there are two ways of producing more lift, or more thrust by that blade. And then both the omega, so the rotations per minute, or rotational frequency, and the pitch angle will drive that, because a higher pitch will also have cause a higher air load, a higher CT, or thrust coefficient. So it's all proportional. And so that is that is proportional to the tip vortex strength. So lowering the RPM, but hiring the blade pitch, for example, and arriving at the same, so you might end up with the same with the same vortex circulation. If I understood the question correctly. So both RPM and the pitch are baked in there, and the higher they are, the higher then the vortex strength of the tip vortex. And then the second question was, how are we conserving the tip vortex in the Lattice-Boltzmann method? I believe, was that the question?
Yes, Professor, correct.
Yeah. So it depending on where's our, so these were all measurements here. Okay, here I have a result for the for the different methods. So you can see that if I go to the laser pointer, not draw. Do you see my cursor?
Yes, Professor, we do.
Okay. So you can see the higher fidelity method here, overflow CFD, that's not Lattice-Boltzmann, but we're using it as comparison, conserves the tip vortices way better than our Lattice-Boltzmann simulation. And so that's a drawback. I'll fully acknowledge that. Could we conserve it better? Probably yes. If we use a finer mesh, because we are then less numerically dissipative. But we want to use the Lattice-Boltzmann, or we are using Lattice-Boltzmann method as a mid-fidelity tool for quick turnaround and up to real-time simulations. And therefore, we're actually not, purposely not resolving the tip vortices here, because if we would go to that mesh resolution, we would actually then result probably at similar, or say several more orders of magnitude of computation expense, and that will then get rid of our mid-fidelity advantage or our quick turnaround times. So at the end of the day, it's about what you want. So just like a lot of numerical methods, Lattice-Boltzmann method is not a panacea either. It has its drawbacks. We're using it as a mid-fidelity tool, quick turnaround, and coarse meshes, so coarsely resolved LES, if you will. And so we're not conserving them as accurately as the higher order methods, period.
Thanks, Professor. We are already out of time, so please everybody join me thanking Professor Rauleder for this presentation. Thank you very much, Professor, for joining us.
Thank you for having me. And yeah.
Thank you so much, Professor.
I have stopped sharing the screen.
Can you hear us?
Yes, I can hear you.
I just wanted to thank you for the really nice presentation.
Yeah, you're welcome. And it was a pleasure speaking with you leading up to the seminar. Thanks for organizing it. I guess I got this email kind of by surprise, because Marilyn Smith, my dear colleague, I guess couldn't make it in time, or she couldn't make the time. But it was a pleasure.
Thank you so much for doing it on such a short notice. It was great. Like all the content was very relevant.
I mean, hopefully the content was adequate for the audience. If I had more time to prepare the slides or the talk, it might have been a bit more concise or a little more clear, but given the short notice, I tried my best.
Thank you so much, Professor.
I saw your face.
Bye.
Bye.
You get coffee from me. When we told you. Exactly. Even the one of the. It's totally named from you now.